your part 2 video for 6.2 definite integrals. This brings us to example 2, evaluate the integral below. So we are looking at the integral from -2 to 2 of the square root of 4 minus x squared. Well, this is something that you should recognize because the square root with just the positive in front of it and not the negative, this is actually the shape of a semicircle. So it's a semicircle that starts at -2, ends at +2. If I plug in 0, I'm going to get 2. And so I have something that looks kind of like that. So I'm finding the area under this curve. So this is not necessarily a problem where you would want to use the standard anti-differentiation techniques. In this case, we want to use geometry to figure out what the area beneath the curve is. So the area of a circle is pi r squared, and since this is a half circle, it's going to be 1/2 pi r squared. The radius here is 2, so this is 1/2 times pi times 2 squared, so 1/2 of 4 times pi, which is going to give us 2 pi. So the area under the curve for this question is 2 pi. So that brings us to another interesting concept here, and that's the fact that whenever your function is negative, whenever your function is below the x-axis, that integral value is going to be negative. And on page 286, they talk about area above and area below. If you're finding total area, and they basically specify that the negative area should be positive, you do want to make sure that you're aware of that, because typically any areas that are below the x-axis, we would actually subtract those out. So that is an important fact to know about area. And then we have theorem 2, the integral of a constant. So if f of x is equal to some value c, where c is a constant, on your integral a to b, then the integral from a to b of f of x is equal to the integral from a to b of c d of x. And when you integrate that, it's the same thing as c times b minus a. Because if you were to graph this c, because it is a constant, it's going to be a straight line. And so if we're going from a to b, this distance is b minus a, this height is c, because that gives you a rectangle, and that would be the formula for area of a rectangle. And so this is used a lot, like this is a word problem that uses this concept. A train moves along a track at a steady 75 miles per hour from 7 a.m. to 9 a.m. Express its total distance as an integral. Evaluate the integral using theorem 2. So my total distance traveled is going to be my integral from 7 to 9 of 75, I'm going to call that dt. So the actual value is going to be 75 times 9 minus 7, which is 75 times 2. So 150 miles is going to be the total distance that's traveled. So area under the curve is not always going to be area, sometimes it is distance, because if you do the antiderivative of velocity, which is this 75 miles per hour value, then you end up with position or distance. Accumulator function is another way we can look at the integral. We have for this one, if the function f is integrable over the closed interval, then the definite integral of f from a to x defines some new function, which is the accumulator function. So this is it's a very similar setup. Notice t is my variable of integration. But I'm going, instead of going from a to b, I would write this as a to x, and that gives me that accumulator function value. And so we're actually going to use that in our next example. And I think you'll get a better idea of how this is used and why we would use it after this. Okay, so let f of t equal 1 plus 2t for 1 less than or equal to t less than or equal to 6. Write the accumulator function a of x as a polynomial in x, where my area, or my accumulator function, is equal to the integral from 1 to x of 1 plus 2t dt, and then again, x is in between 1 and 6. So if we were to graph this, so if I plug in 1 into that function, I'm going to get back 3. If I were to plug in 6, I'm actually going to get back 13. That's going to go a little bit off my graph. So that's going to be up here somewhere. So if I'm looking at this, that would actually be a trapezoid. That's the shape of a trapezoid, is what I'm looking at there. So it's a trapezoid. And again, I'm not necessarily going the whole way from 1 to 6 because it doesn't say the area under the curve. There's some x value somewhere in here. There's some x value in here in between 1 and 6. That's just giving me the limits of that. So that's really what I'm going to be using. I'm going to be appealing to the geometry to actually write the accumulator function for this. This is the formula for area of the trapezoid. So we have to look at what our distances are here. I know that I have a 1 down here on the x-axis, and I'm going to some value x, which means this whole distance here is x minus 1. That is going to be the height. So x minus 1 is going to be the height. So if I come over here to write my accumulator function, my formula is 1/2. I know I'm going to have my base 1 and my base 2 that I'm going to have to add together. And then 1 minus x is going to be my height. Well, base 1, which is this distance, that's merely going to be 3. Because I know I'm starting at 1, so that 3 is not going to change. However, this value, this distance over here, I would be plugging in x into the 1 plus 2t function. So this distance is 1 plus 2x. I guess I should have written that in black, but that's okay. So then to find the accumulator function, we need to simplify this. So I have 1/2 times 4 plus 2x. Distribute the 1/2. So I have 2 plus x times x minus 1. And whenever I multiply those together and simplify, I'm going to end up with x squared plus x minus 2. X squared plus x minus 2. That's actually what you get whenever you take the antiderivative of the 1 plus 2t and put in your x there. The only difference is the minus 2, which is your constant, and I'm not sure that there's a great way to find the constant for that particular function. So that's where this accumulator and using the geometry, why it is so helpful. Okay, lastly, we have how to do an integral on the calculator. So the integral from a to b of f of x dx, well, I guess this isn't lastly, because there is still an example 6 after this. That's going to be your fn int, and then the setup there, that's actually the setup for if you had one of the older black calculators. The newer ones actually allow you to put in integrals as they stand. So we have example 5 here. I'm going to show you how to put the first one in to the calculator. And then for the rest of them, I'm just going to write up the answers of what you should get. I would like you to try these on your calculators to make sure that they work out the way that they're supposed to. So let me pull up my calculator here, if I can find what I'm looking for. Let's see. TI. There we go. So again, we're going to do letter A, which is the integral from -1 to 2 of x sine of x. So let me get back to the main screen here. So if you go to math and down to option number 9, that's your FN int. That allows you to set up an integral. And again, if you have one of the newer calculators, it should look exactly like what I have here. So my lower bound is -1. My upper bound is 2. My equation is x sine of x. I'm going to close that parenthesis there in the x, get out of there. And then I have to define the variable of integration, which is also going to be an x. Hit enter. We would round to 3 decimal places because that's standard for the AP exam. So this one would be 2.043. So 2.043. So take a moment, maybe pause this video and try B and C and make sure you can get those correct. For part B, you should have 3.142. And for part C, 0.886. And also, I guess I didn't really say this, for part A, you do need to make sure you're in radians and not degrees. So you want to make sure, if for some reason you had switched away from radians, that you put it back in radians before you would do that type of question. Our last example in 6.2, we are going to find the integral from -1 to 2 of the absolute value of x divided by x dx. And this is a really great problem because functions that have discontinuities in them, you can still find the area underneath the curve as long as you're aware of where those discontinuities occur. So with this particular function, there's a discontinuity at 0. It's actually a jump discontinuity. Because from -1 all the way up until 0, I would get a value of -1. Obviously, the top is always going to be positive, but you're dividing by the negative of the same number. So that's going to be down at -1. And then from 0 to 2, not including 0, I'm going to jump up to +1. So my function is going to look like that. Well, I can still use geometry and find the area between the curve and the x-axis. I know we always say area under the curve, but it really should be area between the curve and the x-axis. From -1 to 0, that area is -1. It's a 1 by 1 block, but it's below the x-axis, so it's negative. From 0 to 2, that's a 2 block. From 0 to 2, all positives, it's 2 of those 1 blocks. So your total area here is actually going to be 2 minus 1, which is simply 1. I don't know that this is something that would work on a calculator, if they would give you an error because you do have a discontinuity, but it works really great just graphing this out and just using the geometry, really using the geometry, the lines, and the area under the curve, or rather the area between the curve and the x-axis. So that concludes your part 2 video for 6.2. Go back through, rewatch this, rewatch the first video. You can always reach out and ask me questions if you have them. Don't forget there's a book video as well, and we will be continuing our look into integrals as we move through the rest of chapter 6.